Welcome to Lecture Online, and our next topic in modern physics is Compton scattering. And what is Compton scattering? Well, they found out that when a very high energy photon is incident on an electron, kind of collides with an electron, then if the photon scatters off at an angle, let's say theta, or in this case I said phi, with respect to its original direction, and of course, when that happens, the electron will get hit and probably will go in the opposite direction because there's conservation of momentum, which we'll talk about later. Depending upon the size of the scattered angle, the wavelength will change accordingly. And the equation is such that the difference in the wavelength of the scattered photon relative to the wavelength of the original photon, the difference between those two is equal to h divided by mc. Now, mc is, well, that's the mass of the electron, c is the speed of light, times 1 minus the cosine of the angle. And of course, if I keep the angles the same, it makes a lot more sense. Since I used phi there, I guess I'll use phi over here. All right, interesting. So let's say that we have a photon, let's say original photon is equal to, let's make it 0.02 nanometers. Of course, that's a very short wavelength. That's probably kind of in the range of X-rays. So let's say we have an X-ray photon. It hits an electron, scatters off at some angle, changes direction by an angle of 30 degrees. What is the final wavelength of that particular photon? All right, how do we do that? Well, first of all, we want to go ahead and calculate what this is equal to. And we can then say that the final wavelength is equal to, when we move this across, it becomes the original wavelength plus h over mc times 1 minus the cosine of phi. Now notice that it'll be greater than the original wavelength. Greater wavelength means less energy, means there's some energy loss, and that energy loss will then be imparted on the electron, which will then shoot off at some direction with some velocity. And the amount by which the wavelength changes is equal to this. So let's go ahead and calculate what this is equal to. So this is equal to the original wavelength of 0.02 times 10 to the minus 9 meters. That's the original wavelength, plus Planck's constant, 6.626 times 10 to the minus 34 joules times seconds, divided by the mass of the electron, 9.11 times 10 to the minus 31 kilograms. And we multiply that times the speed of light, 3 times 10 to the 8 meters per second. And then we multiply that times 1 minus the cosine of 30 degrees. All right. Okay, so we have 6.626 e to the 34 minus, divided by 9.11 e to the 31 minus, divided by 3 e to the 8. Okay, let's write that down so far. So this is equal to 2 times 10 to the minus 11 meters, plus this quantity right here, which is 2.424 times 10 to the minus 12 meters, multiplied times 1 minus the cosine of 30 degrees. So multiply times 1 minus 30, takes the cosine of that, close parentheses, equals. And so now that becomes 2 times 10 to the minus 11 meters plus 3.248 times 10 to the minus 13 meters. All right. So add those two together. So plus 2e to the 11 minus equals, and this becomes then 2.0325, rounded off, times 10 to the minus 11 meters. Okay, and that's the new wavelength. Okay, so we start out with a wavelength of 2 times 10 to the minus 11. And we end up with a wavelength of 2.0325 times 10 to the minus 11. It doesn't seem like a lot, but definitely the photon has lost energy, and that energy is then imparted on the photon. So here's how you calculate the change in the wavelength and the final wavelength after a photon has scattered off of an electron.